Hello. This is Thriving Dev, and today's quick tip is how to reduce rebalance downtime for stateless Kafka Streams apps by a factor of 450. This video includes a demo where I will show you how adding a single line of config to your Stateless Streams app reduces the downtime from over 50 seconds to less than 100 milliseconds. Afterward, I will thoroughly analyze and provide a detailed explanation on the matter at hand. To let the cat out of the bag, the magic is setting the streams config internal leave group on close to true. The example scenario we're going to look at is a Kubernetes pod to be evicted and then replaced. Let's take a look at our setup. So we have a stateless Kafka Streams app running as a deployment, 3 replicas. We consume some topic with 6 partitions. And we can see 3 pods, 3 consumer instances in a healthy running state with partitions assigned. Now our scenario in step 2, the first pod is going to be evicted, so it's closing down gracefully, stops processing. Kubernetes will schedule and place a replacement pod, which is going to boot up. And in our final step and target state, the new pod will transition to a running healthy state, get an assignment, and start processing. This entire transition from step 1 to step 4 comes with a downtime, which we are going to measure in this demo. And this is the topic of this video, which I call the rebalance partition downtime. Let's see how this works out. Okay, time to get the demo started and see some action. What we can see in the screen is a Grafana dashboard where we have a split screen view. We're going to run 2 versions of our Streams app. On the left-hand side, we will have Streams default config applied. On the right-hand side, we will have internal leave group on close equals true. So we can directly compare the behavior. The top panels show the number of replicas. So we have 3 replicas running. We can see the rebalances, or essentially not. For right now, everything is stable and no rebalance is taking place. Then we can see the consumer lags. You can see the consumer group and topic name and partitions. And at the bottom, we can see our message rate, which is 900 messages per second coming through on the input topic and being processed. We can see on the consumer lag a healthy jitter of data being pulled, processed, pulled again. So this is a healthy behavior, which you should be familiar with. Before we trigger the container restart, let me just state for the record, the scenario is described as a Kubernetes deployment, but the simulation is done on a Docker Compose stack. To the application, it doesn't matter. It's in the end just a container with the Java app running, which is stopped and brought back up. And to the consumer group, this doesn't matter. All the source code, including the producer and the Streams app and the Compose stack, is on a GitHub repo, which I will provide the link in the description below the video. Without further ado, let's trigger this container restart and let's watch what's going to happen. Immediately we can see the number of replicas drop from 3 down to 2. And on the left-hand side, we can see the consumer lag actually is starting to build up. We can see a lag for 2 partitions. On the right-hand side, there's no lag built up at all. We can see rebalances already took place on the optimized setup. So we've had 1 rebalance after the consumer instance stopped and left the group. And then when a new consumer came back, there was another rebalance. Both were very short, so the consumer lag, you just cannot see any downtime in processing. On the left-hand side, we saw the consumer lag starting to build up for 2 partitions, which fits our expectation. We've had 6 partitions, 3 replicas, so one of those consumers that was stopped had an assignment of 2 partitions, in this case partition 1 and 3. So as soon as the consumer stopped, no data was processed, so the consumer lag started to build up. Now the interesting bit is what happened at this point in time, which co-locates with the new consumer coming back up and joining the group. Here we can see the processing stopped entirely, partitions 0 and 3 increasing in group lag, but now all of the other 4 partitions also started to build up group lag. And then we finally had our rebalance and processing continued and the lag quickly dropped. Processing caught up and we are back with a stable assignment and processing data. If we take a look at our processing downtime with the default config, we can see the lag started building up just straight after the full minute, 1 or 2 seconds passed, and we were fully caught up 47 seconds past the full minute, which makes our 45-second window of downtime for partition 0 and 3. And then we have stopped the world processing of all partitions from 19 past to 47 past. On the right-hand side with our optimized config, we can see 2 rebalances took place, but just by looking at the consumer lag metrics, we cannot see any downtime in processing. Now that we have seen what's happening, let's move on to the why and explain that behavior. Let's begin with the optimized application. Here we have a diagram with a time axis. The lower half focuses on what's happening in Kubernetes and the upper half on the Kafka Consumer Group Protocol and task assignment. From a Kubernetes point of view, the pod is terminated, then the replacement pod is scheduled, placed, and the image pulled. The new containers start, the pod is entering a running phase, and the application initializes. Here we start interacting with Kafka, and finally we enter a running healthy state. Then when the pod is closing down, a rebalancing is triggered. Tasks are reassigned to the remaining active group members and processing continues. When the new pod comes up, there's another rebalancing triggered. Tasks are reassigned and we end up with our new workload assignment and even distribution of tasks. Okay, great. This is exactly what we want. We have 2 very short downtimes, less than 100 milliseconds, hardly any delay in processing of our data. And the simple reason for that is that the consumers notify the consumer group coordinator that they're gonna shut down and stop processing by sending a leave group request via the consumer group protocol. And this is the default behavior of any regular Kafka consumer. But coming to our default streams behavior, it's not the default for Kafka Streams. And this is where the big difference comes from. Looking at the code in the Streams config, there's a consumer default overrides where internal leave group on close config is overwritten to false, while for regular Kafka consumers, the default is true. Having this in mind, it's actually pretty straightforward to explain the behavior we have observed in the demo. When the Streams app is closing down and no leave group request is sent to the coordinator, no rebalancing is triggered. So the tasks that were assigned to pod 1 simply stopped being processed. Since the coordinator does not know the status of pod 1, it's considered as unknown. It won't receive any more heartbeats, so it will be aware that something is off, and it will start measuring against the session timeout, which is by default 45 seconds. So only after 45 seconds, a rebalancing is actually triggered that will leave us with a new assignment. So this explains the delay of data processing. Now, what comes on top of this is that the new replacement pod, when connecting to Kafka, is sending a join group request. A join group request would trigger a rebalance, but since the group coordinator is in a state where it doesn't know if pod 1 is still processing or not, it revokes all of the assignment and puts everything on hold until the session timeout runs out. So as soon as our new replacement pod attempts to join the group, all of the assignments are revoked and we end up in this situation where no more data is processed at all. By configuring your Kafka Streams app with internal leave group on close equals true, a graceful shutdown immediately triggers a rebalancing process and tasks are reassigned to other active members within the group. The processing downtime is significantly reduced while also improving elasticity and resilience. As a result, your application enables interruption-free CI/CD and auto-scaling. Please note, the recommendation only applies to stateless streams applications, and internal leave group on close is a non-public config, so it may change without prior notice. And that's all for today. Thanks for watching. You can find all the diagrams on my blog and the source code for the demo on GitHub. Links are in the description. If you liked this content, please give me a thumbs up, subscribe to my channel, and follow me on social media. Thank you, and see you next time.